Welcome everyone. So today we are going to discuss the 13th group elements. The 13th group elements also we call it as Boron family, also called third A group elements. Okay, so let us restart. Yes, the 13th group elements. This is what the first group in the P block elements. In the P block. Yes, what are P block elements? P block elements is nothing but the elements in which the differentiating electron. Differentiating electron means last coming electron. The differentiating electron enters into p subshell, or if the p orbitals are progressively filling, then those elements, all those elements we included in p block. So this is what first group in the p block. Now what are the elements which are coming under the 13 group elements? So those are boron, aluminium, gallium, indium, thallium, and then recently they introduced a new element, that is what, nihonium. Okay, nihonium is what? It's a radioactive element. Okay, so now if you take these elements, boron, aluminium, gallium, indium, thallium. Now in these all, boron is what? It's a rare element and it is black color. Boron is exists as in the black in nature, and it's very hard in nature. So because of its very hard nature, it is less reactive. Because of its very hard nature, boron is what? Less reactive in nature. Whereas the remaining all elements, remaining four elements are what? Metals. Remaining four elements are metals only. Only the one and only the element, that is boron, it's a non-metal. Okay, this is what? Non-metal. And one more thing, the newly introduced element, that is what? Nihonium. Nihonium, and it is a radioactive element. Okay, and whose atomic number is 113 and whose mass number is 286. Okay, so this is about the radioactive element, that is what? Nihonium. So if you check the general electronic configuration, the general electronic configuration of these all elements is ns2 np1. ns2 np1. Okay, so this is about the general electronic configuration. Next, coming to the abundances. Abundances, boron is a rare element, and if you check the next element, aluminium. Aluminium, it is the third most abundant element. Third most abundant element in earth crust. So in overall in earth crust, aluminium is the third most element. Okay, then what about the first two elements? So the first one is oxygen, next silicon, and the third one is what? Aluminium. So this is what in general. Oxygen is more abundant in the earth crust. Thereafter silicon, and the next one is aluminium. Coming to that, aluminium is not only the third most abundant element in the earth crust, this is the most abundant metal in the earth crust. Why? Because remaining the first two are what? Non-metals. The first two are non-metal, then the third one is what? Metal. So this is the most abundant metal in the earth crust. So this is a general introduction about the 13 group elements. Let us start the periodic properties. Periodic properties. In the periodic properties, the first one is atomic size. Atomic size. How the size will change from top to bottom. So when you go from top to bottom, the atomic size will increases with an exception. So there was one exception in case of atomic sizes. What is that exception? So generally in any group, when you go from top to bottom, what happens? The size increases, radius will increases, but here there was an exception. What is the exception? That is what? Boron, gallium, aluminium, indium, thallium. So this is the actual order. Expected order is what? Boron, aluminium, gallium, indium, thallium. But gallium is exceptionally small in size than aluminium. What is the reason? If you take the gallium belongs to what? Third period element. Okay, third critical element means there was an availability of 3d. Okay, 3d orbitals. Okay, sorry, gallium belongs to fourth period, so 3d subshell, 3d orbitals are available. So, but 3d orbitals are large in size. Okay, because of large in size, they are diffuse. Because of its diffuse nature, what happens? The screening effect of these d orbital electrons are less. So, because of less screening effect of these 10d electrons, okay, gallium is what? Exceptionally smaller in size than aluminum. So, this is one exceptional case in case of atomic size. Clear? So, next move to the next periodic property, that is what? Ionization enthalpy. Ionization enthalpy. When you check the ionization enthalpies, IE1 plus IE2 plus IE3, that means the sum of first ionization enthalpies of boron is very high. So because of its very high ionization energies, okay, boron do not exist in the form of +3 form. Okay, so that is why it will forms always covalent compounds rarely. Okay, so this is about the boron. Next, coming to the order of the ionization energy, variation of ionization energy in the group from top to bottom. In general, ionization energy is inversely proportional to size, that we know that. Okay, so what happens in the group from top to bottom? Size increases. If the size increases, general order is what? Ionization energy should decreases. So, but here in the group from top to bottom in the 30 group elements, ionization energies decreases with two exceptions. There was two exceptions here. What are those two exceptions? Okay, let us see. So that is what boron, expected order I am writing first. That is what boron, aluminium, gallium, indium, thallium. So this is what expected order. Expected order, but actual order is boron, thallium, gallium, aluminium, indium. So this is what actual order. Actual order. What is the reason? So here thallium is exceptionally having more ionization energy than the remaining first three. So what is the reason? In thallium, okay, this is what it belongs to sixth period. Now, thallium belongs to sixth period. So there 4f electrons. 4f electrons, that means electrons are present in which orbital? 4f subshell. But the 4f subshell having very less screening effect. Because of poor screening effect, okay, the effect of nucleus over the valence electrons is very high. Because of that highest effective nuclear charge, to remove the electron from the thallium, they need more energy. That is why, because of 4f, okay, because of less screening effect of 4f electrons, the thallium is exceptionally having higher ionization energy. What about the gallium? So as we know, in the gallium, which electrons are there? 4d electrons are there. Oh, sorry, 3d electrons are there. 3. So, but even the 3d electrons, 3d subshell also having less screening effect. So, because of less screening effect of 10d electrons, gallium is exceptionally having more ionization energy than aluminum. Okay, so this is the actual order. This is the actual order of ionization energy in the 30 group. Okay, next let us move to the third one, that is what? Electronegativity. Electronegativity. So here when you check the electronegativities from top to bottom, when you go from top to bottom, electronegativities decreases first, thereafter increases. Okay, it is not following a regular order, irregular order. Okay, so this is the group which is showing almost all periodic properties are irregular, not regular. Okay, see, so if you take the electronegativity, first it decreases, thereafter increases. From where to where it decreases, from where to where it increases. See, if you take the boron, aluminium, gallium, indium, thallium, okay, boron to aluminium it decreases. Boron to aluminium it decreases, whereas from aluminium to thallium it increases. From aluminium to thallium, it increases. That means boron greater than aluminium, but aluminium less than gallium, less than indium, then thallium. So this is what, first from boron to aluminium decreases, thereafter from aluminium to thallium again it will increase. So if you arrange this in a perfect order, what is the first highest one? Boron. Boron is the element which is having the highest electronegativity because of small size and the highest effective nuclear charge. So after the boron, thallium will come. Okay, after thallium, indium, next gallium, and the least one is aluminium. Aluminium is the element which is having minimum electronegativity. Boron is the element which is having maximum electronegativity. So this is what electronegativity of what 13 group elements. Let us move to the next periodic property, that is what density. Density. So density follows a regular order only. There was no problem. Regular order, that is what it increases from top to bottom. When you go from top to bottom, the density will increases. That is what boron, aluminium, gallium, indium, thallium. There was no problem. There was no irregularity. There was no exceptions in case of density. Next one, after the density, melting boiling points. Melting points, let us be check. Melting point. Melting point again it is showing irregularity. There was an irregularity in melting points again. Okay, what is the irregularity? So usually the regular trend is what from top to bottom the melting and boiling point should decreases. Okay, but here from boron, aluminium, gallium, from boron to aluminium, boron to gallium it decreases. Boron to gallium it decreases. Thereafter from gallium to thallium again it will increases. So first it decreases up to gallium, again from gallium to thallium increases. That means which is the element having the least melting point? Gallium. Gallium is the element which is having low melting point, and boron is the element having maximum highest melting point. So if they ask you to arrange the following in the decreasing order of melting points, how you will write? First one is boron, next one aluminium, after aluminium thallium, after thallium indium, and the least one is what? Gallium. So this is what order of melting points. Okay, next coming to the boiling point order. Coming to the boiling point order, it follows the regular order only. There was no problem. In case of boiling point, it decreases from top to bottom. From top to bottom, what happens? The boiling point it decreases. So boron is the element having the highest boiling point because of its very hard nature. Okay, it is having the highest boiling point. Now, out of these all elements, if you check the gallium having high boiling point and very low melting point. Okay, very low melting point and high boiling point. That is why gallium is the element having high boiling range. Gallium is the element having high boiling range. Boiling range. Okay, here then you may get the doubt. What is the reason why boron is having the highest melting and boiling points? What is the reason behind this? Let us see. Boron is having the highest boiling point, highest melting point, and the gallium having the lowest melting point. What is the reason behind that? Let us see. If you look at the structure of the boron, usually boron exists as B12. Okay, B12 means 12 boron atoms combined together in the form of icosahedral form. Icosahedral units. Icosahedral units. In that icosahedral units, the total, this structure is nothing but it has 12 corners. Icosahedral unit means it has 12 corners and 20 faces. 20 faces, and each boron is connected to 5 other boron atoms. So that structure is what? So because of this icosahedral structure, okay, highly packed structure, boron is very very hot. That is why it is having highest melting point. Whereas coming to the gallium, Gallium in general, gallium exists as what? Ga2 unit. Two gallium atoms combined together in the form of Ga2. So because of its Ga2 structure, we can easily break. Okay, so its melting point is least. So that is the reason why boron having the highest and gallium having the lowest melting point. Okay, so this, and because of this highest boiling range, this gallium they are using in a high temperature thermometers to measure the temperatures which are around 300 250 degrees Celsius, high temperatures. To measure the high temperatures, gallium they will use. Okay, so this is about the melting boiling points. And after the melting boiling points, let us discuss oxidation states. Oxidation states of this 13 group elements. So if you if you look at the general electronic configuration, what is the general electronic configuration? Ns2 Np1. Ns2 Np1. So when you go from top to bottom, boron, aluminium, gallium, indium, thallium. Okay. Anyhow, boron is what? The sum of the first three annihilation energies is very high. So that is why the boron will not be exist as a +3. It's very difficult to exist in the form of +3 form. So anyhow, at very high temperature, what happened? It will form covalent compounds. So it is a less react. Okay, you don't consider the boron in this case. Now coming to the aluminium to indium. So aluminium stability, the +3 stability is more, whereas thallium +1. Okay, so that means when you go from top to bottom, what happens? The stability of +3 decreases. The stability +3 stability decreases. When you go from top to bottom, the stability of +3 decreases, whereas the stability of +1 increases. +1 stability increases. That means the stability of higher oxidation states decreases, and the stability of lower oxidation states will increases. That is, what is the reason? That is due to inert pair effect. So that is because of what reason? Because of inert pair effect. Now, what is inert pair effect? Inert pair effect is nothing but, see here, there was a valency s orbital electrons and p orbital electron. In valency S, how many electrons are there? 2 electrons are there. In P, 1 electron is there. Suppose if only 1 P electron is involved, then what is the oxidation state? +1. If both S and P, both are involved, then what is the oxidation state? +3 oxidation state. So now what happened? These S orbital electrons are not, if the S orbital electrons are not participating in the bond formation. Okay, then what is the oxidation state of this? Only +1. And that reluctance means not willing. The reluctance of participation of s orbital electrons in bonding formation is called what? Inert pair effect. So inert pair effect is nothing but the reluctance of participation of ns electrons in bond formation is called inert pair effect. Inert pair effect. You may get the doubt. Why the s orbital electrons are not willing to participating in the bonding form? There are two reasons here. Yes, what are the reasons behind the inert pair effect? Okay, so if you take the first reason, the effect of nucleus on the valency s electrons is very high. Okay, that is the first reason. So the effective nuclear charge means Z effect. The effective nuclear charge on valency ns electrons is very high. Why? Because s orbitals are very near to the nucleus. Because of the very nearest distance, what happens? The effect of nucleus over the valency ns electrons is very high. So that s electrons are not going to participating in the bonding formation. That is the one reason. And one more reason is very important reason. So what is the one more reason? That is the energy required to unpair the electrons is greater than the energy released by formation of two additional bonds. Okay, you just understand this point. There is a huge meaning here. The energy required to unpair the electron is very greater, is higher than the energy released by the formation of additional two bonds. See, let us see that if you check the configuration. See, this is the Ns2 electrons. This is what? Np electrons. So Np, one electron. Suppose if these Ns electrons are not unpaired, then what happens? Only the p electron only will participate. So they exhibit what? +1 oxidation state. So in order to form three bonds, what happens? One of the electrons should excite from Ns to Np. That means here what should happen? Unpairing of electron should take place. So to excite the electron from here to here, to excite the electron from Ns to Np, they need some energy. So the energy required to excite the electron from Ns to Np is greater than. So here already initially how many bonds are forming? One bond. But after the excitation, how many bonds are forming? Three bonds. That means additional how many bonds are forming? Two bonds are forming. So while the formation of the two additional bonds, the energy released. Okay, so the energy required to excite the electron, unpair the electron, is greater than the energy released by the formation of new bonds, two new bonds. Because of that reason, they are not willing to unpair the electrons, participating in the bond. Okay, so this is what we call as inert pair effect. So because of this inert pair effect, okay, if you check the indium, what is the stable oxidation state of indium? +3. Okay, and indium can show +3 and +1, and aluminum also can show +3 and +1, and thallium also will show +3 and +1. Now tell me, indium if you take, what is the stable oxidation state of indium? +3 is the stable oxidation state. That means, suppose if there was an iron +1 if you take, iron +1. But what is the stable form of iron? Indium +3 form. That is why the iron +1, indium +1 is happily releases two more electrons, means happily undergo oxidize and they acting as what? Reducing agent. Understood? Okay, even the aluminum also. When you compare the aluminum +1 and aluminum +3 is more stable as per the inert pair effect. Okay, so if there was an aluminum +1, it is a highly unstable. So if this aluminum +1 is happily what? It releases two more electrons, undergo oxidation and it becomes act as what? It is again reducing agent. Now come to thallium. Thallium plus and thallium +3, which is the stable oxidation state. Thallium +1 is the stable oxidation state. Suppose if the thallium is in the form of +3 state, now the thallium +1 is happily gains two more electrons, means happily it will undergo reduction and act as what? It act as what? Oxidizing agent. Okay, so thallium +3 is acting as a strong oxidizing agent, whereas aluminum +1 acting as a strong reducing agent because of this reason. So sometimes they may ask you among thallium chloride and the thallium Cl3, which is a stable form, which is a stable compound. Definitely thallium chloride, TlCl, because here the thallium is in +1 state. +1 is more stable than +3. Whereas AlCl3, which is a stable form compound, AlCl3, because aluminum +3 oxidation state is stable. So based upon this only we will decide the stability of the compounds. Okay, so this is about the oxidation states. Chemical properties. Yes, in the chemical properties, the first one is action with air. Reaction with air. How they react with air? As we know, the air active components are what? Oxygen and nitrogen. Yes, when you take the boron in solid form, means in crystalline form, boron directly in solid form, it will not react with air, means it will not react with oxygen. There was no reaction. Okay, boron can react with oxygen only in the powder form. Okay, suppose if you make into powder, the boron powder on oxidation means on reaction with air, okay, they forms both boric oxide B2O3 and BNX, that means nitride, boron nitride. So as we know, boron nitride is very hard. It's very hard, and it is like graphite. Okay. Next, this is about the boron. Next, aluminium. If you take aluminium, when aluminium reacts with aluminium, even in crystalline form will not react. What is the reason? So when aluminium reacts with oxygen present in the air, they forms what? Alumina, Al2O3. But suppose this is the aluminium. Okay, so after it reacts with the oxygen, what happens? It forms a protective layer on it, and that protective layer protects the inner aluminium from further reaction. So that is why they forms what? So this is the aluminium. It forms a protective layer, and this protective layer, this is what? Al2O3. This Al2O3 stops further reaction of aluminium with oxygen. So because of the formation of this alumina, okay, it stops further reaction with oxygen. So this is about the action with air, and after that, so whatever may be the remaining elements, gallium, indium, thallium, they will react with oxygen, and they forms what type of oxides? E2O3 type of oxides they form. Okay, if you check the nature of these oxides, so let us here only we will discuss the oxides. So here if you take B2O3, Al2O3, Ga2O3, In2O3 and Tl2O3, when you take this B2O3, it's an oxide of a non-metal. So what is the nature? This is what? Acidic in nature. Whereas the next two, that is alumina and gallium oxide, these two are what? Amphoteric in nature, and the next two are what? Basic in nature. Okay, so this is the nature of these oxides, and if you dissolve it in the water, they give their corresponding hydroxides. Okay, B2O3 on hydrolysis we get boric acid. Al2O3 on hydrolysis we get aluminium hydroxide. Like this, they use their corresponding hydroxides. So this is about the action with air. Next, let us discuss the second chemical property, that is what? Action towards acids and bases. Action with acids and bases. One point, as we know, boron is less reactive because of its hard nature. Because of its less reactivity, it will not react with any acid or base. There was no reaction. Boron do not react with either acid or base. Okay, either in crystalline form or amorphous form, whatever it may be. The boron never reacts with acid or base. Coming to the aluminium, when aluminium dissolve in mineral acids. What are mineral acids? Like HCl, H2SO4, like this. When we dissolve the aluminium in mineral acids, okay, they liberates hydrogen gas. Whereas aluminium is passive towards what? Nitric acid, concentrated nitric acid. So when we add concentrated HNO3, when we add the aluminium into the concentrated HNO3, okay, because of the formation of protective layer, what is the protective layer? Al2O3, it stops further reaction towards concentrated HNO3. That is why aluminium is passive towards HNO3, concentrated HNO3. Okay, next one, aluminium. As we know, aluminium is amphoteric. It can react with both acid and base. So aluminium reacts with mineral acids, liberates hydrogen. Aluminium reacts with bases like NaOH also. Okay, aluminium reacts with base. Here, this is one of the important reaction. We will get sodium meta-aluminate. Let us see how the sodium meta-aluminate we are getting from the aluminium. Let us see. So when aluminium reacts with NaOH, 3 moles of NaOH, first of all we will get AlOH thrice, aluminium trihydroxide, but still it is what? it is electron deficient and act as what? Lewis acid. Lewis acid. So because of its acidic nature, it reacts one more NaOH. It reacts with one more NaOH. Now we will get NaAlOH4. NaAlOH4. This is nothing but what? NaAlO2 plus 2H2. So this is rewriting as what? NaAlO2, sodium meta-aluminate having 2 water molecules, dihydrate. Okay, just remove 2 water molecules from it. Remaining is sodium, 1 sodium, aluminum, 1 aluminum, 2 oxygens will be there. So sodium meta-aluminate 2H2. So this is actually the reaction of aluminum towards base. Okay, aluminum reacts with NaOH, forms aluminum trihydroxide, but it's an electron deficient. Because of an electron deficiency, it is acting as a Lewis acid. Because of its acidic nature, it reacts with one more NaOH and it forms this complex. This is one ionic nature. Immediately transform into sodium meta-aluminate. So this is a reaction of 13 group elements towards acids and bases. Next, third one, the third chemical property, reaction with halogens. Reaction with halogens. When the 13th group elements, E represents what? 13th group elements. When 13th group elements reacts with the halogens, okay, they forms EX3 type of halides. EX3 type of halides. Okay, so this EX3 type of, and the nature of EX3 is different. Some of the halides are what? Ionic. Some of the halides are covalent. Okay, which halides are ionic and which are covalent? Let us see. So when you go from BX3, boron trihalides, to thallium halides, means from top to bottom. Okay, BX3, AlX3, GaX3, InX3, TlX3. What happened? The acidic nature decreases. Very, very important. Acidic strength, the acidic strength decreases. What is the reason? What is the reason? Main reason behind this. So in BX3, the central atom is what? Boron, small size. Because of small size, it has high effective nuclear charge. Because of having high effective nuclear charge. Okay, and this is what? Electron deficient. So that is why the nucleus will always trying to attract the electrons more. That is why BX3 is more acidic than TlX3. So the reason is acidic strength decreases due to increasing the atomic sizes. Due to increase in the atomic sizes, the acidic strength decreases. Okay, this is what in case of trihalides of 13 group elements. And sometimes what happens when we compare BF3, BCl3, BBr3, BI3. Okay, this is also one of the most important question. When we go from boron halides, from one boron fluorides to boron iodides, what will be happen to the acidic strength of them? So if you take boron belongs to which group? Okay, boron belongs to 30th group, and which period? Second period. So that is why here 2p and 2p overlapping. So what is the pi bond here? 2p pi bond. Here 2p 3p pi bonding is there. Here 2p 4p pi bonding. Here 2p 5p pi bonding is there. 2p 3p 2p 4p 2p 5p. Okay, now so because of this is what pi bonding, back bonding. What is the relation between acidic nature and back bonding? Acidic nature, acidic strength is inversely proportional to back bonding. Back bonding. The acidic nature and back bonding, they both are inversely proportional. I mean the compound where more back bonding, whose acidic strength is less. The compound where less back bonding, whose acidic strength is more. Now tell me, so 2p overlapping is more than 2p 3p, than 2p 4p and 2p 5p. Because of strong overlapping, there was a more back bonding in case of BF3. If there was a more back bonding, then its acidic strength less. That is why BI3 is more acidic than BBr3, then BCl3, then BF3. So usually the people do the mistakes here. So whenever which among the following is more acidic means first they will go to the option BF3 only. But in fact, when you compare the halides of boron, Ba3 is more acidic than remaining all other halides. So BF3 less than, BCl3 less than, BBr3 then less than Ba3 because back bonding decreases. The back bonding decreases, acidic nature increases. So this is one of the most important concept. Next, let us move to the stability of the halides. Okay, as we know, when you compare the BCl3 and AlCl3, which is more acidic, as we know, BCl3 is more acidic. Why? Because in the group when you go boron to aluminium, gallium, indium, thallium, what happens? Acidic strength decreases, that we discussed here. That is why when you compare the BCl3 and AlCl3, BCl3 is more acidic. Acidic nature means what? The tendency of accepting a pair of electrons. So because of its more tendency, the BCl3 is always having the tendency to accept the electrons from ammonia like ligands, and they forms NH3, A2 bond, BCl3. Like this, BCl3 always gains electrons from ammonia. Whereas in case of AlCl3, AlCl3 gets stabilized by dimerization. So it was stabilized by dimerization. No need, as like BCl3, the AlCl3 is electron deficient one. In BCl3, why it is accepting electron? Why? Because the octet, its octet configuration was not came. BCl3 surrounding the boron, 3 bonds are only there, 3 2s are 6 electrons only there. To get the stability, to get the 8 electrons, you need 2 more electrons. That is why it is Lewis acid. Similarly, in AlCl3, Al also not getting octet configuration, but it is getting stabilized by dimerization. Let us see the dimer structure of AlCl3. That is Al. So this is a dimeric structure of AlCl3. So in this dimeric structure here, in this dimeric structure, each aluminum is surrounded by how many chlorines? 4 chlorines, 4 bonds, 4 2s are 8. So because of this dimerization, what happened? Both the aluminiums are getting stable octet configuration. Now here in this structure, not only AlCl3, the compounds which are having this kind of structures, one point. So these are the terminal bonds. These are the what? Bridge bonds or central bonds. So the bond angle between these terminal bonds, let us consider this is X, you consider. Okay, and whereas the bond angle between these middle central halogens is Y. And when you compare this bond angle and this bond angle, always X is greater than Y. X means terminal bond angle. The bond angle between the terminal bonds is always be greater than the bond angle between the bridge bonds. What is the reason? Why? Because the terminal bonds are free. They can easily move from one place to another place. Because of this freeness, what happened? The bond angle is very high. Whereas in case of bridge bonds, what happened? It was constructed. It was fixed. Because of this, what happened? The bond angle is less. And one more thing, if the bond angle is less, then the bond length is more. Means bond angle, bond length both are inversely proportional. So here, if X is more, then this terminal bond length and the central bond length, okay, let us consider this is A and this is B. Now when you compare the A with B, which is longer? B is longer. These 2 points you should why? Because bond length is inversely proportional to bond angle. Okay, so here the terminal bond angle is greater than central bond angle. That is why terminal bond lengths are lesser, shorter than bridged bond lengths. So this is not only applicable for AlCl3. The compounds which are in the same structure like AlCl3, for all these compounds, this rule is applicable. Remember this. Okay, this is about the reaction towards halogen. Now, one more thing, hydrolysis. For example, suppose if you hydrolyze a BCl3 on hydrolysis, what happened? All 3 chlorine have been replaced with OHs. So what we will get? BOH3. So what is the name of this one? Orthoboric acid. orthoboric acid. Okay, this on further heating, suppose if you heat orthoboric acid still is an electron deficient and it accepts one more OH minus and it forms what? BOH4. So what is the structure of this one? Tetrahedral structure. Tetrahedral structure. So the question is, when BCl3 on hydrolysis, what is the units we are getting? What is the units we are getting? Tetrahedral units we are getting. Now, whereas AlCl3, if you hydrolyze the AlCl3, we will get AlOH6 plus 3. So octahedral units we will get. Octahedral units. This is the main difference between BCl3 and AlCl3. BCl3 and hydrolysis we get tetrahedral units, whereas AlCl3 and hydrolysis we get octahedral units. So this is about the chemical properties of 13th group. Let us discuss anomalous behavior of boron. Behavior of boron from 13th group elements. That means what is the different behavior of boron from the other group members? What is the main reason why boron is showing the differences from the other group members? Because boron is small in size, because of its small size, and because of its high ionization energy, and because of its high effective nuclear charge and its non-metallic nature. So because of these all reasons, boron is showing some differences, anomalous behavior from the other group members. What are those anomalous behavior? The first behavior is boron is a non-metal, whereas remaining all metals are what? Metals. That is the first difference. And the next difference is the oxide of boron is acidic, whereas oxide of aluminium and gallium, these two are what? Amphoteric. Whereas remaining indium oxide and thallium oxide, they both are what? Basic. So this is one more difference. Okay, next the maximum covalency of boron is what? Maximum, how much here? Tetrahedral unit only. Because of unavailability of d orbitals, the boron is permitted to maximum 4 bonds only. So the maximum covalency of boron is 4. Whereas others, the maximum covalency of other metals like aluminum, if you take 6. Because of availability of d orbitals, they can extend their covalency to 6 or more than 6 also. So this is about some anomalous behavior of boron from other group members. Okay. Next, similarities. Similarities between boron and silicon. Similarities between boron and silicon. Why? Because boron is a 13th group element, boron, aluminium, and silicon is carbon, silicon. So diagonal relationship. Because of diagonal relationship, boron and silicon, they both are showing the similarities. Okay, what are the reasons why they are both are showing similarities? Because their sizes are same sizes, and their polarizing power also same. Okay, and their ionic sizes are same, and their polarizing powers are same. And one more reason is what? Because their electronegativeness is also same. So because of these three reasons, boron is showing the similarity with silicon. Yes, what are the properties which are similar to both boron and silicon? The first property is both boron and silicon, they both are showing allotropic behavior. The first one is both boron and silicon, they both are showing the allotropic behavior. Next one, both the oxides of boron and silicon, they both are what? Acidic in nature. This is the second property. Both oxides of boron and silicon, they both are acidic. And what is the third similarity? Suppose when you react these oxides B2O3 or SiO2 with carbon, okay, when the oxides of these elements are reacts with carbon, they form the corresponding carbides. So what are the carbides here? B2C will come, and here B2C3 will come, okay, and B4C3, and this is what SiC. SiC is what? Covalent in nature, very strong, aggressive. Okay, this is what when these oxides are reacting with the carbons, they form what? Carbides. They are forming their corresponding covalent carbides. Next, one more similarity is when these elements, okay, when boron or silicon, when they react with magnesium, boron forms borides. That is what Mg3b2 borides, and the silicon also forms silides. That means Mg2Si. Okay, so they both are forming the covalent compounds. And similarly, when these oxides on hydrolysis, we are getting boric acid H3BO3, whereas SiO2 on hydrolysis, so we are getting what? Silicic acid H2SiO4. So this is one more similarity. So on hydrolysis, both oxides of boron and silicon are forming their corresponding acids. And one more similarity is when the boron halides BX3 on reduction with the LiAlH4, lithium aluminum hydride, they are producing their corresponding hydrides, means boron hydride, borane. Here borane will come. Okay, 2BH, that means B2H6 will come, plus LiCl plus AlCl. Similarly, SiX4 on reduction with the Al lithium aluminum hydride will get silane, SiH4 will come. So these are the few similarities between boron and silicon. Once again, they both are showing the allotropy behavior. Both oxides are acidic nature. Both oxides react to the carbon forms carbides. Both elements are reacting with magnesium and they form the corresponding borides and silides. And both oxides on hydrolysis getting acids. And both halides on reduction with the lithium aluminum hydride we are getting hydrides. So these are the similarities between boron and silicon.